Oh. Yeah, I hope I actually had the right camera. Let me fix that. Ah, there we go. Good evening and happy Monday. We will be finishing up with the limits this evening. That is the goal. Right. So you should have seen, we're looking at limits at infinity for the first block. And then we're going to go ahead and in the second block, look at the formal definition of the limit. Now, this is going to involve proofs, specifically a lot of epsilon delta proofs, which is going to be very tricky for a lot of students because it's going to be your first look at rigorous mathematics. Now, the good news about that is it's only going to be like a FYI kind of thing. I'm not quizzing you on it. I'm not testing you on it, right? So there's going to be no questions on either a quiz or a test asking to provide an epsilon delta proof. I don't even think I assigned a MyOpen Math homework assignment for it. So let's get started. So I'm going to get started with actually two limits that are not at infinity, but involve infinity. These really should have been thrown in with the algebraic limits we did, what was it, Thursday in the A block? I just missed them. All right, so here we go. We take a look here. Limit as x approaches 3. X squared minus 11x plus 30 over x cubed minus 4x squared minus 3x plus 18. What are we going to get if we just plug in 3? It looks like, what, 9 minus 33 plus 30, so it'll be negative 3 plus 9, which is 6. Plug in 3 in the denominator. What is it? 27 minus 36. Negative 9. Right? And then negative 9 plus 18 is 9. We get 6 over 0. This is not indeterminate. Right? Technically speaking, this means the limit does not exist. But that doesn't really give us a lot of information. Whenever there is a 0 in the denominator, that generally means you're going to have a vertical asymptote. We want to now look at the one-sided limits. All right, so let's look at from the left. Okay. Well, I actually never did check. See what my personal one was. Just to make a note to do that. Oh, that's this file, huh? Oh, okay, well, I'll just keep using this, whatever. So I'm going to show you how we can use mathematical factor. I'll also show you the command on the calculator, the TI Inspire CX2. So it's fairly straightforward. There. Yep, there it is. It's just the factor command, right? So the command is really just factor. And just type in the expression you want factored. Then you just shift enter to execute, and it gives you the factored form. X minus 3 squared times x plus 2. And it'll make sense why I'm factoring the denominator shortly. Okay? On the TI Inspire, 2 ways to do it. You can just write out factor. And then your expression. Right? Or if you want, if you don't want to worry about trying to type out on the keyboard, just menu, algebra, and then you'll see factor. And it's just the same thing. Right? And if you're absolutely opposed to technology, right, you can factor it by hand. I think this one's actually, is it? You might be able to factor this one by grouping. Maybe not. Right, but you studied how to do that in pre-calculus. Right, the idea is this. All of our values are going to be less than 3. Right, so you put in a value close to 3 but less than it. Negative squared is positive. This is obviously going to be positive, right? Because remember, we're close to 3. You have a positive times a positive, which is positive. The numerator itself is positive. So this is infinity. Right? You can easily verify that if you want by creating a table with values. Right? And seeing that your denominator is going to keep getting smaller and smaller and smaller the closer you get to 3 on the left, but it'll always be positive. You want to do the same thing with a right-handed limit. Well, again, squared is always positive times positive. This is also positive infinity. Right? So it's a vertical asymptote that on both sides, the function will go up to infinity. So what we can say is this limit here, we can just say equals infinity. Right? Notice that the two one-side limits are doing the same thing. Right? For lack of a better term, they're equal. Right? Okay, I'm going to throw this one in as well. Again, this should have been done on Thursday, but oh well. I'll look at it now. So again, this form, right? Some constant over 0 does not mean indeterminate. That's why I didn't factor the numerator. There's no need. The only reason I factored the denominator was to make it easier for me to see on each side am I going to positive infinity or negative infinity. If you take a look at this second one, if we plug in 3, we'll get 9 minus 27 is negative 18 plus 18 is 0. 9 minus 3 is 6 minus 6 is 0. This is 0 over 0, which is indeterminate. Right, so remember, we're going to try and find a function that is identical to this one everywhere except at 3. So do algebra, completely factor the numerator and denominator, see if we have any like terms. Okay, what do we get? 6 and 3 both minus. Here we get 3 and 2. 3 is negative. we'll get what? -3/5. Right. So this is to emphasize, again, you want to always try substitution first and see what you get. If you get a value, right, like 8/3 or 23, right, then obviously you're done. That's your limit. If you get a number over 0, non-zero number over 0, that is itself an answer, right? But it means that your limit either is positive or negative infinity or just straight up does not exist, right? It's a vertical asymptote. What are you doing on either side? Right, so that's where we would then check the two one-sided limits to see how it's behaving. Zero over 0 is indeterminate. That is when you have to do algebra. Okay. So let's take a look at now limits at infinity. So limit as x approaches infinity of x cubed plus 2x squared plus 1 divided by x minus 5. Again, try substitution. And I use that term substitution again very lightly because infinity is not a value you can just plug in. So we're going to look at this. Start with the numerator. Okay. Take an extremely large number and cube it. It's extremely large, right? It's even larger. Take an extremely large number, square it, and then double it. It's again an extremely large number, an infinitely large number, if you will. We're taking the sum of two infinitely large numbers, which is, again, really, really large. It's infinitely large. Now you add 1 to it, it's still infinitely large. So let's say the numerator is infinitely large. Now, what about the denominator? Take an infinitely large number. Take an extremely large number and subtract 5. So let's say you have $40 trillion in the bank. You go out and you make a $5 debit purchase. Do you even notice it in your bank? No, right? It doesn't really affect you at all. So you take an extremely large number and just subtract 5. It's still extremely large. So you get infinity over infinity. This is indeterminate. Right. And what I'm going to do is, let's go ahead and list out all of the indeterminate forms. Right, so we had 0 over 0. Infinity over infinity. More specifically, right, plus minus infinity over plus minus infinity. Infinity minus infinity is indeterminate. That's what I thought. Just wanted to double check. One raised to infinity is considered to be indeterminate. Infinity to the 0 is indeterminate. Zero times infinity is indeterminate. And finally, zero to the 0 is indeterminate. If direct substitution yields any one of these 7 forms, then you have to use some type of algebraic manipulation. Oh, that's new. They apparently updated Teams. You can actually zoom in on the shared screen now. That's actually very useful. The manipulation that we are going to do here is a little bit different than if we got, say, 0 over 0. Now, once you're extremely comfortable with how functions behave, then you should easily see what this limit is. So algebraically, here's what we're going to do. Focus on the denominator. Since we're dealing with a polynomial, you want to factor out the largest term. Which is x. We're left with 1 minus 5 over x. This x, right, or this term that we just factored out, we're going to move it to the numerator. Right? Remember what happens when you move a term to a numerator. Or vice versa, you move from the numerator to the denominator. You just make the exponent negative, right? Now distribute. We'll have x squared plus 2x plus 1 over x left in the numerator. So 2 important limits. but I can really write as a single limit. Right, you have 1 over x to the n. I want to write this. Now, for positive n, the limit of that as x approaches either positive or negative infinity is 0. Right? What that, of course, means is if we look back over here, this 1 over x goes to 0. This 5 over x also goes to 0. Using limit laws, we can say now that this is what we're left with. Should be careful. Because technically it's not equals. I'm going to say it behaves like this limit. Well, this 1 doesn't matter, right? This numerator, as x continues to grow, x squared plus 2x is also going to continue to grow, right? So it's going to grow without bound. So this limit is infinity. This limit is infinite.
What was the reasoning for why you were able to cancel the 1 over x and the minus 5 over x?
So I'm not technically canceling them, right? But what's happening is as x continues to grow without bound, isn't 1 over x just going to go to 0, right? You're 1 over a number that keeps increasing. So that tends to 0, right? And that's the same reasoning for why 5 over x goes to 0. Right, so that just comes from, this is an important limit over here, right? So 1 over x to any positive power will always go to 0 as x either goes to positive or negative infinity.
Okay, thank you.
Right? Let's move this up a little bit. So if we take a look at x approaches infinity limit, x cubed plus 2x squared plus 1 over now 5 minus x. We can be a little cheeky here. We don't have to do a lot of work. Factor out a negative. Oops. If I factor negative out the denominator, it just flips the denominator, right? So instead of 5 minus x, it becomes x minus 5. But isn't that the limit we just did? So take an infinitely large number, right? The largest number you can think of. Multiply it by -1. It's now a really large number in the negative direction, right? So this is negative infinity. Do not like that infinity. There we go. I wonder if that was supposed to be x squared. No, I'm not changing it. Limit x approaches negative infinity. X cubed plus 2x squared plus 1 over x squared minus 5. Right? We take a really large number in the negative direction, cube it. It's still a really large number in the negative. Right, so if you will, this kind of looks like negative infinity. Take that same number and square it, and then multiply by 2. It becomes like a positive infinity, right? And then this 1, right, just in terms of what's going to happen, this 1 really doesn't matter, does it? We're dealing with infinitely large numbers. 1 just doesn't really matter. Oh dear. We have negative infinity plus infinity. Well, that is not 0. Right? Here's how we look at it. What has a larger impact? Cubing or squaring? Right? Here's how we're going to look at it. Or here's how we're going to think about it. Let x be much larger than 2. Right, so I'm only looking at absolute values here. X cubed would be x times x squared, right? But we just said that x is much larger than 2. So that would be much larger than if I replaced one of the x's with a 2. Right, try it out. Go with 100. 100 cubed is what? So it'd be what? 10 squared cubed, which is 10 to the 5th? 100,000? Ten squared. I'm sorry, 100 squared. 10,000. I'm sorry, be a million. 100 cubed would be 1 million. 100 squared is 10,000. 20,000. Well, 1 million is definitely much larger than 20,000, right? So even though we have infinities, you can think of this infinity as being much larger than this infinity. The magnitude of it, right? So we have a much larger infinity being multiplied by -1 plus a much smaller infinity This infinity dominates. The limit of the numerator is negative infinity. See that? Now, luckily, the denominator, that -5 just doesn't matter. That's infinity. So this is indeterminate. So we play the same game that we did before. Look at the denominator and say, so it's a polynomial, right? What is the largest power? Right? In other words, what is your leading term?
X squared.
The x squared. We're going to factor that out of the denominator. We factor it out, we're left with 1 minus 5 over x squared. Move that x squared up into the numerator. Distribute that x to the -2 through, right? So we're distributing the numerator. We're left with x plus 2 plus 1 over x squared. Right, the 1 over x squared and the 5 over x squared are going to tend to 0. So really, we can think of this limit as just the limit as x approaches negative infinity. Right, of x plus 2 over 1. But again, since we're over 1, we can really just think of it like x plus 2. So you take a really large number in the negative direction and add 2 to it. All right, so let's say, I'll do a an all too real subject for just about everyone here. You have $200,000 in student loan debt. You make a $2 payment. Did you even make a dent in your loan?
Definitely not.
So that limits negative infinity. And in fact, with loans, it then buffs out that dent with the interest, right? So it's like, yeah, that $2 didn't do crap. Right, so that's how you kind of think of these limits now at infinity. Right? Think of it that way. Now, again, these are simple because we're only dealing with rational functions. I'm just going to throw this in here just for completion's sake. But you can see I'm using a similar argument as I did before. Say that limits positive infinity. All right. Now we've got our feet wet, let's kind of go further in. Let's look at one that now involves a radical. Limit as x approaches infinity. Square root of 9x to the fourth plus 3x plus 2 all over 4x cubed plus 1. It shouldn't be difficult to see that this gives you the indeterminate form infinity over infinity. So I'm just going to skip writing it. So look at the denominator. Factor out the leading term. Right? You actually don't have to factor out the entire leading term. I'm going to. If you want to, you could just factor out the x cubed, and you'll get the same thing. We're going to be left with 1 plus 1 over 4x cubed. Move it up. A few ways you could look at that 4x cubed to the minus 1. Right, it could be 1/4 x to the minus 3 or 1 over 4x cubed. Right? We still want to distribute that term through. Okay. But how are we going to do it? Right. So in other words, if I want to move that term, that 4x cubed inverse, inside the radical, we have to do something to it first. So think of the square root of 8. It's the same as 2 square root of 2, right? Well, how did we get that? Well, we realized, right, that 8 is 4 times 2. And what we can do with square roots is, if you take the square root of a product, you can actually split it right across the product. So that's the same as root 4 times root 2. But root 4 is 2. And that's how we get the 2 root 2. But the beautiful thing about equality is it works both ways. That means that 2 square root of 2 is also root 8. And then what we can do is we can work backwards. Right? So if I want to move this 2 inside the square root, notice that we squared it first. So that's what we have to do here. We have to square this term first. Then we can put it inside the square root. So we can now write this square root for x cubed to the minus 2 right, and then times that 9x to the 4th plus 3x plus 2. Okay. Well, 4 squared is 16, right? So that 4 to the negative 2 acts like 1 over 16. X cubed squared would be x to the 6th. So this term would be 1 over 16x to the 6th. Without doing any kind of simplifying of fractions, When we distribute that through, what we're left with under the radical would be 9 over 16x squared plus 3 over 16x to the 5th plus 2 over 16x to the 6th. Any term that has a constant numerator and a positive power of x in the denominator is going to go to 0. So this limit behaves as the limit as x approaches infinity of 0 over 1. And that limit is just simply 0. Okay. Well, let's take a look now at a case where the radical is now in the denominator. Right. Again, it should be fairly simple to see that you're going to get infinity over infinity. Take a look at what's under the radical. We want to factor out the leading term. Right, so 25x squared, right? So the square root of 25 is 5. What is the square root of x squared?
X.
Okay. let me. How do I want to do that? I think it'd probably be easier to do it this way. So by show of hands, and by hands I mean just click the raise button. Right, you should see my frame is now yellow with my hand up. I unclick it and it goes away. So show of hands, who agrees that it's X? And then when you raise your hand, please keep it up so I can take a count. Okay. So I have 8 who agree that it's X. So you can go ahead and lower your hands. So I notice that one person in the meeting already outed themselves as having me for pre-calculus in the introductions. You know who you are. They didn't raise their hand. So what's the square root of 4?
Two.
Square root of 2 squared then is what? It seems obvious, right? 2? What about the square root of -2 squared? What is that square root? It's also 2, right? Which is not -2. If I say x is -2, the square root of x squared is not x. This is a very common mistake. square root of x squared is actually the absolute value of x. See that? Because by definition, the square root of a number always gives the positive root, never the negative, right? So the square root of 4 is 2, not negative 2. So that is very important to remember. So when we go and factor the 25x squared and we take its square root, it's 5 times the absolute value of x. And you're going to see why that's important. All right, now we do the same thing. We want to move that term up to the numerator. We now want to distribute it through. But now we have a problem. Off this term. I mean, it makes sense that it goes to 0 regardless, right? But algebraically, why does it go to 0? Right. The limit I gave you was for positive powers of x, not absolute value of x. Here's what we have to do. So remember back, it was Thursday evening, right? We looked at a limit involving absolute value. Right, what do? We replace the absolute value with the appropriate function, right? Either positive x or negative x, depending on what we were approaching. We're approaching infinity. If x is approaching infinity, then what can we say about the values of x? Specifically, how do they relate to 0?
They're above 0, they're positive.
They're positive values. We replace the absolute value of x with positive x because of that. This is why that absolute value is important. Because if we were approaching negative infinity instead, we wouldn't be replacing absolute value of x with positive x, would we? No, we replace it with negative. Which means your answer would probably be off by a negative. In fact, in this case, it's guaranteed to be off by a negative, right? That first term in the numerator would be negative 4/5 if x was approaching negative infinity, not positive 4/5. Now we can go, that term's going to go to 0. That term's going to go to 0. So this limit's behaving as the limit of 4/5, which is just 4/5. All right. Right, same idea, except now we're writing it in rational exponent form. Okay. So again, look inside the 1/3 power. We're going to factor out that leading term, that 8x to the 4th. And we're left with 1 plus 1 over 4x to the 4th. We factor out that 8x to the 4th, right? So we do that by distributing the 1/3 power through to each term. We're going to have an 8 to the 1/3. What is 8 to the 1/3 power? Right? What was it?
2.
2. One third. It's an odd indexed radical, which means I don't have to worry about absolute values, right? Cube root of 8 is 2. Cube root of negative 8 is negative 2. Which means the cube root of 2 cubed is different than the cube root of negative 2 cubed. You actually do get x out of that. So I can just write that as x to the 4/3. Oh, I forgot the limit. To the power of technology, I can just move that off to the side and write in my limit. All right, we're going to move that 2x to the 4/3 up to the numerator and distribute it through. Numerator is going to be left with 1/2 minus 9 over 2x, right? X to the 4/3, I'm sorry, x to the 3rd over x to the 4/3 is just 1 over x. Which means that term goes to 0, as does that term. So what we have is essentially the limit as x approaches positive infinity of just 1/2, which is 1/2. Okay. What about this one? Limit as x approaches negative infinity. Absolute value of x plus x all over x plus 1. But we're approaching negative infinity, right? Which means all of our values of x are going to be less than 0. Well, isn't that just the limit of 0? which is just 0. All right, I'm just checking, just looking something up. No, okay. Yeah, let's take a look at this one. Okay. So something that I didn't mention last Thursday. Now that we have the idea of continuity, right, what it means for a function to be continuous. And I don't think it necessarily applies here. Maybe it does. It does. Not to this problem, but to the next one. The composite function theorem. So suppose we have some function f of x that is continuous at the value g of a. And we're also going to say that the limit as x approaches a of g of x is g of a, which equals L. Then the limit as x approaches a of f of g of x is equal to f of L. With this, we can do direct substitution regardless of the function. As long as it's continuous, right, at g of a. This is very useful. Right. The idea then becomes, what we do is we look and we go and we try direct substitution. Well, you can see we're going to have a problem. Because we try direct substitution, look what we get. We're essentially going to have what? It's going to be of the form infinity over infinity. So we take a side note, we go, okay, well, what does this limit actually equal? We go, what is the leading term? Negative x, right? Factor it out. Going to have negative x minus 9 over x in the numerator. And that is negative infinity, right? So here's what we do. We do substitution. Or not substitution, I'm sorry. We do change a variable. So let's say that theta is x squared plus 9 over 9 minus x. As x approaches infinity, we just saw that theta approaches negative infinity. Then these two limits are the same using change a variable. So now we just look at it and we go, what is this limit? Actually, oh, no, that's right. Okay, it's the inverse tangent. So remember the range of the inverse tangent, minus pi over 2 to pi over 2. Think of tangent within that range. Something like this, isn't it? So notice that this one-sided limit is negative infinity, right? As we approach negative pi over 2 from the right-hand side, tangent goes to negative infinity. This means that this limit would be negative pi over 2. Are there any questions so far? Okay. Went slightly long. That's okay. So we'll go ahead and take our break. We'll come back at 7:50. So I'll see you all then. All right, and we're back. We're going to look at one more before we move on to formal definitions, which I may just decide to skip entirely. All right. Take a look at this limit. Right? Limit as x approaches infinity of 1 plus x over 1 minus x. But we're going to proceed the same way. Factor out the leading term in the denominator. Move it up to the numerator. Now distribute the numerator. Those terms go to 0. And what we're left with is essentially the limit of -1, which is -1. Right? So ask yourself, is the inverse tangent function continuous at -1? That is -1 in the domain of the inverse tangent? So what do we think? Is -1 in the domain of the inverse tangent? What is the domain of the inverse tangent? Who remembers that from pre-calculus? Uh-oh. Oh dear. Well, let's see. 1. Three of you make me very sad. It's one of the last things we did last term. It's all real numbers. So that means -1 is in the domain. Inverse tangent is thus continuous at this limit. Right? This limit's going to be the inverse tangent of -1. And the inverse tangent of -1 is -π/4. Okay. Okay. All right, so what I've decided to do is, I think I'll just go ahead and skip, not cover the formal definition of the limit. And for those of you interested, you can just go ahead and view the video that's posted on MyOpenMath. instead, I'm going to look at some additional problems from the textbook, starting with what we just covered, limits at infinity. And I'm glad that I did. Right? So if or when the limit as x approaches either plus or minus infinity of a function is equal to L, right? Then we call that line y equals L a horizontal asymptote. So that's the formal definition of a horizontal asymptote. Right, here we're asked to evaluate the two infinite limits and determine the horizontal asymptotes. We're going to split this up into two limits. This first limit is 3, right? But this second limit is 0. So our limit is 3. I do that, whatever. Well, likewise, if we're approaching negative infinity instead, we can still split it. That first limit is still 3. That second limit is still 0. So our function has a single horizontal asymptote. right? It's y equals 3. No, I do not want to do a proof. Okay. Again, 2 limits we want to evaluate. Start with positive infinity. Algebraically, here's what we do, right? Remember, factor out the leading term of the denominator. We're going to be left with 1 minus 4 over 5x plus 7 over 5x squared. Move that leading term up to the numerator. Distribute it through. Right? Every term that has an x in the denominator is going to wind up going to 0. We're essentially left with the limit of just 3/5. And that limit is 3/5. Same function, except now we're approaching negative infinity. Well, isn't all of the work going to be the same? Which means this limit is also 3/5. Okay. Factor out the leading term of the denominator. Be left with 1 plus 6 over x. Move it up to the numerator. Distribute it through, so to do that, we have to first square it, and then we can put it inside the square root. Uh-oh. This isn't good. There we go. Right. Terms with x's in the denominator, of course, go to 0. That essentially leaves us with the limit of root 3, which is just root 3. This one's good. Okay, so this one is a little bit different. Let's try substitution. So e to the x. So what happens to e to the x as x continues to grow without bound?
Keeps getting bigger.
Mm-hmm. E to the x also grows without bound. Right? So in other words, let's write it up here. This limit is infinity. So we get 3 times an infinitely large number minus 4. It's just infinitely large. Same argument for the denominator. So we do get indeterminate form. All right. We're going to do something that's very similar. Except now what we want to do is we want to look at, instead of a leading coefficient, because we're not dealing with a rational function anymore, we look in the denominator and we go, of those terms in the denominator, which is the largest? 5e to the x or 2?
5e to the x.
That's what we're factoring out. Right. Then as before, move that up to the numerator. Right. Remember, you do that by raising it to a negative power. Distribute that through. All right. Now think of what happens. So we already know that the limit of e to the x is infinite. Right? It's going to keep growing without bound. So what do you think is going to happen to 1 over e to the x?
Gonna put it to 0.
It's going to go to 0. Right? You have 1 over a number that keeps increasing without bound. So those two terms that have e to the x in the denominator are going to go to 0. What we are then left with, in a sense, is just the limit of 3/5. And that limit is 3/5.
Can I ask a question really quickly?
Yes, what's up?
Okay, so for all of these, I've noticed, like, isn't there a more intuitive, I guess, like, less rigorous solution where you realize the constant terms in the numerator and denominator, like, don't meaningfully affect the end behavior of a function, and so you can just kind of like drop them, and then you just factor or like solve from there, like, really easily. So
You
like
can,
this case,
yes.
so in this case, so like in 3 e to the x minus 4, like -4 doesn't actually impact the end behavior of 3 e to the x as we approach infinity, and same in the denominator, so it's just 3 over 5.
You
Like by
can,
cancel.
yes. Right, and
Okay.
that's exactly what's happening. So this is just, like you said, the more rigorous, the algebraic way of doing it to show each step. Right, so to kind of show why that's happening. But yes, if you realize, if you just look at that and go, oh, well, that's obviously 3/5, I'm okay with that. Be careful, though, because if you don't show work, right, and let's say you know it's 3/5, but you accidentally write like 3/4, you get no credit because there's no work shown.
Okay, got it. Thank you.
Right, so just be careful when you do that.
Yeah.
All right. Now, same function, except we're going to let x go to negative infinity. Well, again, try to direct substitution first, right? And again, I use that in air quotes. Well, let's examine what happens to e to the x if x goes to negative infinity. Okay. Well, what do we think is going to happen? So e is being raised to a larger and larger number, but negative now. So what do we think is going to happen?
Go to negative infinity.
So you say negative infinity. So then I ask you, can e to a number ever be negative?
I suppose not.
So it can't be negative infinity because that would imply that e to something is negative, right? Which we know it's not. Well, here's a simple way of looking at it. Do a change of variable. Let y be negative x. So as x approaches infinity, what is y going to tend to? Well, I guess I should say instead of infinity, it's going to be negative infinity, right? So if x is tending to negative infinity, what is y tending to? Be negative infinity, wouldn't it? Which is positive infinity. Right, so now it's the limit as y approaches infinity of e to the negative y, isn't it? Which is the same as 1 over e to the y. And what did we say that limit was? Zero. That makes this limit 0. Right, the other way you can look at it is from pre-calculus. And just remember how e to the x behaves, right? Has a horizontal asymptote at 0. And we know that it's going to hug the x-axis on the left side, right? And it grows without bound on the right side, which would make this limit have to be 0. Right? Well, doesn't that mean that those two terms go to 0 right off the bat? Left with negative 4 over 2, which is just negative 2. See that? So by the way, what is that limit? And so as x grows without bound, how does the natural log, or in fact, how does any log function behave? Right, so I don't actually have to make this just natural log, right? I can make this log base b. So what do we think? So try a chart. Just do natural log. No. Let's do log base 10, let's say. So we'll do the common log. So if x is 10, what is log of x? Or in other words, what is log of 10? And again, remember common log, base 10. Remember what it is? Okay, it's 1. What about 100?
Two.
Let's skip a few. What about 1 million?
Six.
Let's skip a few more. What about a Google? Which is 10 to the 100th.
$100.
Be 100. Starting to see the pattern? What about a Googleplex? Which is 10 to the 1 to the Google. So 10 to the 10 to the 100. If you don't have it, you're overthinking the problem. Be a Google, wouldn't it? What do we notice? as we let x get larger, what's happening to the log? Isn't it also getting larger? Right? It's also increasing without bound. It's never stabilizing to a specific value. Now, granted, look how slowly it's rising. Right? Just to get to 10, we have to look at 10 to the 10th power. Right, which is what, 10 billion? So it increases extremely slowly. But it does increase without bound. And that is true of any base. I should specify any base larger than 1. Right, because if we're between 0 and 1, actually, the log will go to 0. Since natural log is the most common, what do we think the limit as x approaches negative infinity of natural log of x is going to be? And I've already given away a very huge hint, if you notice it. No? The limit does not exist. This limit also does not exist. So even if we approach 0, the limit does not exist. And this is because zero is not in the domain. I'm going to write it this way. Domain of natural log of x. However, if we look at the right-handed limit at 0, we get negative infinity. right? So remember, this is the graph of natural log of x. Okay. Couple more to think about. What is the limit as x approaches infinity of sine x?
Does not exist.
Does not exist. Why?
Because it stays in between 1 and -1. Bouncing back and forth.
Right? It oscillates between -1 and +1. So, real quickly then, what about cosine of x? Be the same thing, wouldn't it, for the exact same reason? And in fact, this is true even as we approach negative infinity for both of them. And in fact, none of the trig functions have n behavior, because all trig functions are periodic. For tangent, just happens to be minus infinity to positive infinity from minus pi over 2 to pi over 2, right? So then every pi, it goes back to minus infinity to positive infinity, right? So to say it oscillates isn't technically correct, right? But it is repeating all of its values. Okay. Are there any questions on limits? No. Okay. That concludes our discussion of the limit. Right, so you have the fourth assignment that'll be due in 2 days, so the 19th. Right, you also have your first report, so an application of the limit. That is also due the 19th. And the test on limits, the Unit 1 test, due before the start of our next meeting. Let me take a look. So the first test is 7 questions. Oh, that's what was going on. I was in the wrong view. Okay. Right, fairly straightforward. Make sure you read each question, okay? Because I did specify how I wanted them to be evaluated, either numerically or algebraically. That's obviously if it says numerically, you have to create a table of values. Algebraically would be what we just spent the last 2 days doing, just essentially substitution. And if you get indeterminate, you have to do algebra on it. I think there's a couple of graph questions as well. Right, so reading a graph. All in all, very straightforward. I think it's a very, very simple test. Maybe one question on there is a little bit tricky, and of course, I typically design my test that way to have one question on there that is the butt kicker. I did give you a hint for it, though. Okay, I just want to make sure that I have the report set to be due at the end of the day. I'm pretty sure I do. Yes, I do. So the report isn't due until the end of the day. The test is due at 6 p.m., so keep that in mind. What we're going to do next time. All right, so it is Wednesday. We will start the derivative. All right, so we'll look at the definition of the derivative. We're going to work with the definition. We're going to see how much of an absolute pain it is Then we're going to start looking at shortcuts for finding the derivative. As a friendly reminder, and I'll remind you every day leading up to it, the 26th and the 27th, that is next Wednesday and next Thursday, there will be no class because I'll be in the hospital with my daughter. There's also not going to be any kind of like assignments or material to do on your own because the way that I have it set up, I don't need to do that. So you can essentially just think of those like free days. Right, I suppose the absolute worst case scenario is if I fall behind, which I don't think I'm going to. I can kind of use those days for catch up. If I need to, I'll just I'll make a recording of the problems I couldn't finish and I'll just post them. That'll be an absolute worst case scenario. So think of those days as kind of like catch up days if needed. But then the following Monday, the 31st, we get right back into the swing of it. All right, so again, do not forget, your first test is due Wednesday. That's the 19th at 6 p.m. before class starts. Of course, you have a 15-minute grace period. Anything turned in after 6:15 will not be accepted. No quiz because there's a test. So that's it. Everyone have a wonderful rest of your night. I will see you again on Wednesday at 6 p.m.
Thank you.
Thank you.
Thank you.